try to be quick. So I'm going to motivate the issue first. This is going to build on, I think, Mark's talk very well. I agree that the future is heterogeneous. And I think there's one particular type of heterogeneity that might be interesting to security folks. There's a lot happening in this area in architecture and increasing with systems and certainly circuits. There's a lot of work in this area. So I think we all know that computing is bottlenecked by data. And today's systems are very processor-centric. If you want to process the data, you need to bring the data into the computing unit. That could be your favorite CPU, GPU, FPGA, etc. And everything else doesn't do anything. And I think it's also well known that it's all about the memory. This is Big Sites writing about his favorite alpha processor in the 1990s that he designed, he and his team designed. And he basically concludes the article saying that over the coming decade, memory subsystem design will be the only important design issue in microprocessors. This is my own PhD thesis, basically on a lot of workloads and Intel processors at the time. Intel used to design. Most of the time is spent on L2 misses. This is Google's data from 2015 on the state-of-the-art processor that they use in their data centers, of their data center workloads, all of their data center workloads. The processor is waiting for data. Most of the time, it's not doing any useful work, basically. And this is another data point from Bill Daly. You can argue with these numbers. If you look at computation, that's 64-bit relative to the floating point operation, that's 20 gigajoules. This is DRAM access, 16 nanojoules. So there's an 800x difference. You could optimize it. You cannot get it below 2 orders of magnitude difference basically today. And if you actually look at a simpler operation, a simpler integer add, still 32 bits. Compared to a DRAM access, the difference is even larger, 6400x. And if you go to storage, if you compare the energy of an integer addition to a storage access, that number goes to 10,000x plus, basically. The question is basically, if we actually want to save energy, does it really make sense to bring the data to the processor? Or does it really make sense to do the computation somewhere else? And this we've written some papers with Google where we show that in real workloads, most of the energy is really spent on moving data across the memory hard. That's 60% over here. But in large machine learning models, it actually goes up to 99%. Almost 100% of the energy of the system is spent on moving data. Okay, so what is the problem? Basically, the problem is we're processing data far away from the data. And what's happening more and more in the field right now is that people are trying to enable computation with minimal data movement. They're trying to compute where it makes sense. And architectures are hopefully becoming more data-centric going into the future. So where does it make sense? I think if you, data actually comes in to the system through sensors, and then it gets stored in storage, and goes into DRAM, and goes into this SRAM chip, which is the processor, right? Essentially, we should be doing processing everywhere, I would say. Everything else other than the processor is dark, which means that you cannot do processing. Does it really make sense to do that? Can we actually distribute the computation across the system? So if you actually take this to the, like we discussed this a little bit in the breakout group, if you actually take this to maybe like 30 years down the road, maybe all of these things that we design in our system should be distributed agents that are capable of computation, and we should not have a special CPU. CPU should not be different from anything else in the system. Everybody should be able to do computation. And everybody has different characteristics on how they can access data clearly. But we're not going to take it that far. Existing models actually think of memory as an accelerator. We're building lots of accelerators, except they're all bottlenecked by this memory bus. Can we actually have some accelerators on the close to the memory side that's not bottlenecked by this memory bus? And again, what is that accelerator is interesting. I'm going to talk about that briefly. But there are many, many open questions here. So the processor can actually, many applications may benefit from it, including machine learning. But we can store data in the memory side, and we can query. The processor can send queries saying, memory, can you execute this function for me on this data? And the memory sends results. Clearly, there are a lot of issues that I'm not going to go into over here. People are actually trying to solve these issues across different levels. And there's progress. That's the good part. And there are actually different types of processing in-memory accelerators. Most of them are processing near memory accelerators today. The second one, actually, Chris mentioned earlier. I'm going to talk about that a little bit, but I'm not going to focus on that. I think there are security issues in all of them. What is processing near memory? Today, you have a processor and then a memory. Near memory means you bring the processor closer and closer and closer and closer and closer. Processing could be anything. It could be any type of logic, basically. The key is memory and logic are separate. They could be near each other though. Processing using memory is fundamentally different. You have processor, memory, forget about the processor. You have memory, and this memory actually has analog operational properties that you could use to do computation. This is a completely different model, and I think it's fascinating. This is happening in both DRAM as well as emerging memory technology as well as SRAM. I'm not going to talk about that. This is harder to accomplish, but I believe there's actually a lot of interesting things that could be done over here also, and maybe security properties of this is really different, like that was mentioned. Okay, so the good news is there are things happening in industry, and perhaps security researchers can play with some of these things. So I'm going to ignore the top part over here. I think there's a lot of interesting things that's going to happen with 3D stacking. But UpMem, which is a French startup, they introduced these DRAM chips where next to each DRAM bank, you can have processors. And essentially, you can offload computation to these processors. And you can buy these. They have an SDK, they have a simulator. It's actually fun to play with. We've been playing with it. I'd be happy to share our experience. We've been writing papers on it, benchmarking, etc. It's not just UpMem. Samsung, SK Hynix, and Alibaba introduced modified DRAM chips where they can accelerate machine learning or recommendation inference. So these are all near memory. They all have next to each DRAM bank within a DRAM chip processors. But in this case, it's accelerators. In this case, the general purpose processor that is fine-grained multi-threaded. There are also other prototypes that look like this. I think you can have access to this actually if you talk to Samsung nicely. Let's say Samsung and Meta together develop this chip. BIM. In this BIM, you have a buffer chip. Buffer chip is an FPGA. And then FPGA, you can have essentially that FPGA access to these huge amount of memory. Again, the reason they designed this to accelerate recommendation efforts. So why am I telling you all this? I think, well, there's a lot more actually in this paper that we wrote. I think there's a lot of interesting things that can be explored from a security perspective. So once you have a system like this, or a family of systems that look like this, what happens to security? I'm not going to go through all of these, but can PIM actually worsen security? Are there new side channels that we need to deal with? Are there hardware bugs that may happen? Can it enhance security also? I think actually it could work both ways, frankly, because you could actually do, you could have less exposure of data because you're not moving the data a lot into the CPU. You could have in-memory encryption, cryptographic hashing we've been discussing earlier. You can execute security functions. There are actually a lot of security primitives that you can implement in DRAM today. These are real DRAM chips, by the way. You can actually abuse the timing parameters in real DRAM chips to get true random numbers, for example, or pops, etc.
Just out of curiosity,
sure.
Has all of the work that has gone into profiling DRAM for RowHammer undermined the, say, use of DRAM to generate random numbers because you've discovered a lot more structure that wasn't previously listed there?
Yeah, that's a great question. So if you want to generate random numbers in DRAM, you should protect it from RowHammer. Basically, if you're able to do RowHammer while you're generating random numbers.
Access like RowHammer by like discovering that like certain cells just don't flip easily and that there's additional structure there, does the randomness kind of dissipate?
Yeah. So basically, we did some work in this area, and we found out that you need to profile the DRAM to figure out which cells are actually good random number generators. And once you profile and figure that out, those cells remain as very good random number generators. You need to take into account temperature effects. So at different temperatures, the profile changes a little bit. But we can actually do it with real DRAM chips. Okay. I mean, I don't have much more to talk about. Oh, yes, please. I absolutely agree. Basically, these are process variation effects, and you need to profile for different kind of cells. Yeah.
Well, you mentioned the power bottleneck and the bus bottleneck, and I wonder how much of this power is because there's a bus, and how much is because there's never none on the other side.
Yeah. So
it basically reduces only the transfer, does it? Reduce the physical fact that there's DRAM there, and you need to open rows, power up the amplifiers, and refresh.
No, certainly. Well, depends on the type of it, right?
Yeah.
If you're doing processing near memory, you're still doing activations, pre-charges, etc. But the bus is a huge bottleneck, actually. The large interconnects that you need to go through to connect the CPU to the memory is the larger bottleneck.
It doesn't matter what you put on the other side of the bus, the presence of a bus.
Yeah. And then, of course, if you eliminate the bus bottleneck, the rest of the stuff becomes a bottleneck, right? But if you're doing processing using memory, if you're doing analog operational properties, exploiting that, then you actually get rid of even more power bottlenecks. So that's a lot more energy efficient, of course, right? If we can afford it. Yes.
I was going to ask basically the same question, but I'll reframe it slightly. So you had, this is about 20 slides ago now,
That's the first slide, you know, there's 21.
you get 20 nanojoules for the DRAM operation on the value slide, right?
Yeah, let's go to Bill Daly's slide.
How much of that 20 nanojoules is the bus versus how much is the actual intrinsic?
Yeah, that's
And
it.
the reason this matters, right, is because it sets an upper bound on,
Yeah.
like, if we can only ever make it twice as good, because only half the, you know,
Yeah.
then like, it's a lot of software sort of change, so
Yeah.
we get twice as good.
Yeah, it's not going to be 12. So a lot of it is the boss actually.
Yeah.
But don't take these numbers with a grain of salt because these are old numbers. These numbers have been like this for a long time. Basically, even though exact numbers change, the differences don't change. And again, this is a very heavy arithmetic operation, right? If you compare this, you get 800x, but
Just
most-
clarification.
yeah.
When you say most of the energy is actually coming from the bus, do you mean like the DQ bus proper, or like all of the wiring down to like the cells of a particular array?
I would say the bus between the memory controller to
And the
the
CPU.
to the DM. Yeah.
Okay.
So if you actually have 3D stacking, that reduces a lot of that energy. But now that energy goes to the TSVs, through silicon vias. It depends on how efficient your through silicon vias are.
But
And a lot of the time it goes on that. Yes.
By most, you mean 51% or do you mean 99.9%?
Oh, I mean, it really depends, right? It usually, I would say it's more than 50%, but it's not 99%. Because DRAM, when you activate, you actually consume a lot of power over there as well. Yes. So it really depends on the workload, how many activations you're doing. What if you're streaming through memory, actually DRAM doesn't consume a whole lot of power, but the bus consumes a lot of power, for example. Yes.
Just to add to that, like you can actually amortize it, right? Because now you have an 8 kilobyte row that's open, and you don't need to be bottling by your 64-bit bus to feed it out. 85 by 8.
Well,
Even if like the cost is same, but if you can amortize it significantly, that's still worth it.
I didn't understand this. How would you amortize it? Maybe we can just.
Like transferring 8 byte by 8 byte over the bus, even is super expensive, right? But if you are just performing operations at
On the memory side.
Yeah.
Yeah.
8 kilobyte then that.
Yeah, exactly. On the memory side, basically, yeah, the buses you need to transfer byte by byte, etc. 64 bits, whatever that your bus currently is. But if you're operating on 8 kilobytes on the DRAM side, you already opened the 8 kilobytes, so you can actually do a lot more operations. I think that makes sense. Okay, and that's all I wanted to have. If people want to talk, I'm happy to talk more. Yes.
That many of these distributed sensors everywhere, they use wireless communication. And so you have the same problem. They're transmitting data from local sensors wirelessly to where it's been going to be computed upon, especially with sensor. And it's the same for do I do local microcontroller in my sensor? Maybe then I need more encryption, and so I need more calculations and so on. And so all supported on magnitude, depending on the right. And that will be the best.
Makes sense.
All right.
All right, thank you.